Look up at the night sky, at those countless points of light, and you see a map of destinations. For centuries, that is all they have been: distant, unreachable goals separated by a terrifying and empty void. The very idea of traveling between them has always demanded a vision of immense power, of monstrous rockets burning for years on end to push a tiny ship across the light years. But what if that entire picture is wrong? What if the cosmos is not a vast, empty desert, but is instead woven through with a hidden system of pathways, a network of invisible highways that could carry our spacecraft across the stars, not with brute force, but with graceful, natural efficiency? This is not science fiction. It is a revolutionary new paradigm for space exploration, grounded in the fundamental laws of physics, and it promises to unlock the galaxy in a way we are only just beginning to imagine. Think back to the great age of sail, when explorers did not simply point their ships at the horizon and start rowing. They learned to read the ocean itself. They discovered the trade winds and the ocean currents, these powerful, invisible rivers flowing through the sea. By understanding these forces, a captain could journey across thousands of miles with astonishing efficiency, letting the world itself provide the momentum. Now translate that idea to the scale of the universe. The fabric of space-time, as described by Einstein, is not a static stage. It is a dynamic, flowing landscape, warped and curved by the immense gravity of stars, black holes, and galaxies. These curvatures create slopes and valleys, currents and streams in the cosmos. They form a complex, interconnected web of gravitational pathways, the invisible highways guiding autonomous spacecraft across the stars. This is the future of interstellar travel, a future where we become cosmic sailors, not cosmic bulldozers. In this video, we will embark on a journey to understand these stellar roadways. We will delve into the mind-bending physics that creates them, from the gentle slopes of Lagrange points to the powerful currents flowing between entire star systems. We will explore the advanced technology required to map these unseen routes and the sophisticated artificial intelligence needed to navigate them autonomously over voyages that could span generations. We will confront the cosmic hazards and the profound philosophical questions that such a capability raises. By the end, you will see how this concept transforms interstellar travel from a distant dream into a plausible, systematic endeavor. This is about more than just building a faster engine. It is about learning to read the map the universe has already provided for us. The greatest voyage in human history awaits, and it begins with understanding the invisible roads that will take us there. To truly grasp this idea of cosmic highways, we first need to shift our entire perspective on what space actually is. For centuries, we've pictured it as a vast, empty stage, a silent, black backdrop where stars and planets simply exist. But that picture is fundamentally incomplete. Thanks to Einstein's revolutionary theory of general relativity, we now understand that space is not a static stage at all. Instead, it's a dynamic, malleable fabric, intimately woven together with time itself into a single entity we call space-time. And the presence of any object with mass or energy, from a tiny asteroid to a colossal galaxy, causes this fabric to warp and curve. Picture a taut, stretchy rubber sheet. If you place a heavy bowling ball in its center, the sheet will sag dramatically, creating a deep depression. Now, roll a marble across that sheet. Instead of traveling in a straight line, its path will bend, curving around the bowling ball's depression. This is a simple analogy for how gravity works. The bowling ball's mass warps the sheet, and the marble follows the contours of that warp. In our universe, the Sun is that bowling ball, warping the space around it, and the planets are the marbles following curved paths we call orbits. They aren't being pulled by a mysterious force. They are simply moving along the natural curvature of space-time created by the Sun's mass. This warping effect creates a complex, invisible topography across the cosmos. Just like on Earth, where we have mountains, valleys, and plains, the fabric of space-time has its own highs and lows, its own gradients and contours. A star creates a deep, smooth valley. A planet adds a smaller dimple within that valley, and where these gravitational fields interact, they can create incredibly subtle and complex shapes, gentle ridges, winding passes, and even stable, flat plateaus. It is within this intricate landscape that our invisible highways are found. These are not paved roads, of course, but preferred routes, paths of least resistance where the energy required to travel from one point to another is significantly reduced. A spacecraft that learns to ride these gravitational contours can, in a sense, coast along them, much like a sailboat catching a favorable ocean current. It's a far more elegant and efficient method of travel than simply fighting against the cosmic terrain with brute force propulsion. We already have a perfect, real-world example of this principle in action, the gravitational slingshot or assist. Think about missions like Voyager or Cassini. To reach the outer planets, they didn't carry enough fuel for a direct flight. Instead, mission planners designed a trajectory that sent them swinging past larger planets like Jupiter. As the spacecraft approaches the planet, it falls into its gravitational well, accelerating dramatically. Then, as it swings around and escapes, it gets flung away at a much higher speed, like a ball rolling down a hill and up the other side. The planet's gravity has effectively given the spacecraft a powerful, free push. This isn't a trick, it's a direct application of navigating the curved geometry of space. The spacecraft is simply following a path that was already there, a natural pathway created by the planet's mass warping the local space-time fabric. This maneuver is a single, simple interaction on a local scale, but it proves the core concept: the universe is filled with these natural gravitational pathways. The next logical step is to ask what happens when we start connecting these local pathways together, weaving them into a vast, system-wide network that could carry us across the solar system and beyond. So if space-time is this flowing, dynamic fabric with its own hills and valleys, who are the primary architects shaping this cosmic landscape? The answer lies with the most massive objects in the universe. Every single thing with massa, from a pebble to a planet, warps space-time a little, but it's the true heavyweights that carve out the most significant features. Stars, black holes, and entire galaxies act like cosmic sculptors, creating profound gravitational wells. Imagine a star not just as a ball of light, but as a massive weight sitting in the center of a vast, invisible depression. The heavier the star, the deeper and wider this well becomes. Planets orbit within this well, tracing paths that are essentially the contours of the curved space around their sun. These wells are the fundamental basins of attraction, the starting points for our invisible highways. But the real magic, the places where these highways begin to form intricate networks, happens where the gravitational fields of two massive bodies meet and interact. This brings us to one of the most elegant concepts in orbital mechanics, the Lagrange point. Named for the mathematician Joseph Louis Lagrange, who discovered them in the 1700s, these are specific, precise positions in space where the gravitational pulls of two large bodies, like the Earth and the Sun, create a perfect balance with the centripetal force needed for a small object to orbit in sync with them. Think of it as a celestial sweet spot. In any system of two large bodies, there are 5 of these points, labeled L1 through L5. 3 of them, L1, L2, and L3, are located in a line connecting the two large masses. They are points of metastable equilibrium, like a ball balanced perfectly on the tip of a very sharp hill. A slight push in any direction will send it rolling away, but with minimal effort you can keep it there. These points are incredibly useful, but they require a bit of active control to maintain a stable position. The truly fascinating points, however, are L4 and L5. These form the third point of an equilateral triangle with the two large masses. If you were to draw a line from the Sun to the Earth, and then construct an equilateral triangle off that line, the points where the other two corners would be are the L4 and L5 points. These are not just points of balance, they are points of deep, stable equilibrium. Picture a ball resting at the very bottom of a wide, smooth bowl. If you nudge it, it will just roll gently back to the center. This inherent stability makes L4 and L5 natural cosmic parking garages. We see this in our own solar system with the Trojan asteroids, which orbit the Sun in the same path as Jupiter, clustered around its L4 and L5 points, trapped there by the stable gravitational forces. These Lagrange points are far more than just theoretical curiosities. They are the crucial interchanges, the bustling orbital intersections on our cosmic highway system. A fantastic real-world example is the James Webb Space Telescope. It didn't just go into a simple orbit around the Earth. Instead, it traveled 1 million miles away to orbit the Sun-Earth L2 point. Why? Because from that unique vantage point, the telescope can keep the Sun, Earth, and Moon all behind it, using a single sun shield to block their light and heat, providing the perfectly cold, dark environment needed to peer into the deepest reaches of the universe. It's a stable orbital position that requires very little fuel to maintain, making it an ideal base of operations. This is a perfect demonstration of using a natural feature of space-time for a practical, revolutionary purpose. It shows that these nodes are not just abstract ideas, they are real places we can use right now. And if we can use one, we can start to imagine connecting them, creating a web of low-energy pathways that link these stable points across the entire solar system. Now, if a single Lagrange point is like a bustling orbital interchange, then the interplanetary transport network is the entire interstate highway system connecting them all. This is the grand, system-wide web of low-energy pathways that crisscross our solar system. Think of it not as a set of straight lines drawn between planets, but as a complex, three-dimensional lattice of gravitational contours, a labyrinth where the walls are made of invisible forces. These are the routes that allow a spacecraft to travel from, say, Earth's orbit to the orbit of Jupiter, not by burning enormous amounts of fuel in a direct shot, but by making a series of carefully calculated swings past the Moon, around Earth, and through various Lagrange points, essentially surfing the gravitational landscape with minimal propulsion. The paths are not intuitive. They are winding, looping trajectories that might seem to take the long way around, but they do so because they are following the natural flow of space-time, the path of least resistance. The mathematics behind these routes is rooted in chaos theory. They exist within what scientists call the stable and unstable manifolds of the Lagrange points. In simpler terms, imagine L1, that metastable point we discussed, as a high mountain pass. There are natural pathways that flow toward the pass and pathways that flow away from it. These are the manifolds. A spacecraft can be inserted onto an inbound pathway, which will carry it effortlessly toward the Lagrange point with almost no fuel. Then, with the tiniest of nudges at just the right moment, it can be transferred onto an outbound pathway that will send it shooting off toward another destination in the solar system. It's a bit like a roller coaster. The initial climb up the first hill requires energy, that's our rocket launch. But once you're at the top, the rest of the ride is a masterful exchange of potential and kinetic energy. You plummet down hills, gaining tremendous speed, then use that momentum to climb the next rise, slowing down as you go. The interplanetary transport network is a cosmic roller coaster where the hills and valleys are made of gravity, and the spacecraft simply coasts, trading speed for position in a beautiful, energy-efficient dance. This isn't just a theoretical concept, we've already used it. A perfect example is NASA's Genesis mission, launched in 2001. Its goal was to collect samples of the solar wind and return them to Earth. Instead of a simple round trip, Genesis utilized the interplanetary transport network. It was sent on a complex 3-year journey. First, it traveled to the Sun-Earth L1 Lagrange point, a fantastic location for collecting pristine solar wind. But it didn't just stop there. It orbited around L1 in a special halo orbit, and then, when the time was right, it used a minuscule amount of fuel to slip onto a return pathway that gently brought it back to Earth. The entire mission was a breathtaking demonstration of navigating these invisible currents. The spacecraft's trajectory was so finely tuned by the gravitational dynamics that its re-entry capsule was designed to be caught mid-air by helicopters over the Utah desert, because it wouldn't have enough fuel for a powered landing. While that recovery had a famous mishap, the navigation itself was a brilliant success, proving that we can already harness this network for sophisticated solar system exploration. The profound implication here is that efficient travel within our own celestial neighborhood is not a future fantasy. It is a present-day reality, at least for robotic missions. The interplanetary transport network effectively turns the solar system from a collection of distant, hard-to-reach targets into a single, interconnected system, much like a well-developed archipelago with regular ferry routes. This changes the economics and feasibility of space exploration dramatically. Instead of designing a massive, fuel-guzzling spacecraft for every mission, we can design smaller, smarter probes that are essentially hitchhikers, catching rides on the gravitational currents that are always flowing around us. This network provides a scaffolding upon which we can build a true spacefaring infrastructure, with reusable pathways that can be traversed again and again. But if such an intricate web of pathways exists within the gravitational influence of our single sun, it forces us to ask an even more exciting question. Could a similar, vaster network exist on a galactic scale, connecting not just planets but entire star systems? So we've mastered the art of surfing the gravitational currents within our own solar system, using the interplanetary transport network to travel between planets with remarkable efficiency. But this is just our local neighborhood. What happens when we set our sights on the ultimate frontier, the vast, empty-seeming gulfs between the stars themselves? Can the principles that work so well around our sun be scaled up to create interstellar highways? The answer, emerging from advanced theoretical models, is a fascinating and promising yes. The galaxy is not a random scattering of stars, it is a structured, dynamic system, and within its overall gravitational field, natural pathways for travel almost certainly exist. The first step is to think about what creates a Lagrange point on a small scale. It's the balanced interaction of two gravitational fields like the sun and a planet. Now let's expand that idea to an entire galaxy. Our Milky Way is a colossal collection of hundreds of billions of stars, all orbiting a common center of mass, which is dominated by a supermassive black hole. But it's not just stars. The majority of the galaxy's mass is actually in the form of dark matter, which creates an immense, invisible gravitational halo. This entire system, the stars, the dark matter, the central black hole, combines to create what astrophysicists call the galactic gravitational potential. This is essentially the shape of the deepest, most fundamental gravitational well in our cosmic vicinity. It's not a simple bowl. It's a complex, spiraling landscape of gravitational hills and valleys on a scale so vast it's almost impossible to visualize. Within this galaxy-wide potential, stars are not moving independently. They travel on vast orbits around the galactic center, and just like planets within the solar system, their gravitational fields interact. While the distances are immense, the gravitational influence of a star, especially a cluster of stars, extends far into space. Theorists suggest that where the orbits of star systems are in resonance with one another, meaning their orbital periods are related by a simple ratio, like 2 to 1 or 3 to 2, stable gravitational corridors can form between them. These are the interstellar equivalents of Lagrange points. They wouldn't be single, pinpoint locations, but rather extended regions, winding tunnels of space where the combined gravity of the galaxy and the surrounding stars creates a pathway of relatively low energy. A spacecraft entering one of these resonant corridors could, in theory, be channeled from one star system toward another, carried along by the large-scale flow of the galaxy itself. The potential benefit is a dramatic reduction in the energy required for interstellar travel. Consider a direct flight to a nearby star like Proxima Centauri, about 4.2 light-years away. With conventional propulsion, you would need to accelerate halfway there and then decelerate for the second half, a process requiring staggering amounts of fuel. But if a gravitational pathway exists, the voyage could be completely different. You might launch from our solar system onto an inbound path toward a local gravitational node. A tiny burst of thrust could then kick you onto an outbound pathway that flows directly toward the Proxima Centauri system. You wouldn't be fighting the galactic gravity, you'd be riding it. The journey might take just as long in terms of calendar years, but the crucial difference is that your spacecraft wouldn't need to carry the immense mass of fuel required for constant acceleration and deceleration. It could be a lean, intelligent vessel designed for endurance, not power. Some mathematical models even suggest these pathways could act as cosmic shortcuts. The winding route along a gravitational contour might actually be shorter in terms of the energy required than the straight-line distance would imply. It's analogous to how a sailboat traveling on a zigzag course against the wind can still reach its destination faster and more efficiently than a motorboat trying to power directly into the wind and waves. The spacecraft is taking the path of least resistance through the complex topography of the galaxy. This doesn't break any laws of physics. It simply uses them in the most sophisticated way possible. The travel time between stars might still be measured in centuries, but it changes the mission from an impossible feat of engineering into a patient, calculated journey along a pre-existing celestial route. This vision of a connected galaxy is breathtaking, but it immediately presents us with a challenge of almost unimaginable scale. How do you map something you cannot see? Mapping these interstellar highways is perhaps the greatest cartographic challenge ever conceived. We are not trying to chart visible landmarks. We are attempting to trace the subtle, invisible contours of gravity itself across tens of thousands of light-years. To do this, we will need an entirely new class of observatory, instruments of almost unimaginable precision designed to read the faintest whispers of the cosmic fabric. The first and most crucial tool in this endeavor is advanced astrometry, the science of measuring the precise positions and motions of celestial objects. Imagine trying to map the gentle slopes and valleys of a landscape by watching how millions of tiny marbles roll across it over centuries. That's essentially what next-generation space telescopes will do. Missions like the European Space Agency's Gaia Observatory have already begun this work, cataloging the positions of over 1 billion stars in our galaxy with astounding accuracy. But the next step requires a leap in precision so great it borders on the unbelievable. We need telescopes capable of measuring the apparent shift in a star's position by a few micro-arcseconds. To put that in perspective, that's like standing on Earth and measuring the width of a human hair on the surface of the Moon. This microscopic level of detail is necessary because it's not the star's position we're after, but its tiny, rhythmic wobble. A star with a system of planets, or one moving through a region of uneven gravitational pull, will not travel in a perfectly smooth line. It will jiggle and sway ever so slightly. By tracking these minute deviations in the motion of millions of stars, we can perform a kind of cosmic tomography, inferring the underlying mass distribution, the dark matter halos, the unseen rogue planets, the gentle gravitational gradients that shapes their paths. This data would allow us to construct a three-dimensional map of the galaxy's gravitational potential, revealing the highlands, the valleys, and the smoothest, most energy-efficient passes between them. But astrometry, for all its power, only gives us a static picture, a single frame from a movie that has been playing for billions of years. To understand the dynamics of this landscape, to see the currents flowing and the pathways evolving, we need a tool that can feel the vibrations of space-time itself. This is the domain of gravitational wave astronomy. When massive objects like black holes or neutron stars spiral into each other, they don't just send out light, they send out ripples in the very fabric of space-time, waves that travel at the speed of light, stretching and compressing everything in their path. Observatories like LIGO and Virgo on Earth have already detected these ripples, but the future lies in space-based detectors like the Laser Interferometer Space Antenna, or LISA. Planned for launch in the 2030s, LISA will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by laser beams. By monitoring the infinitesimal changes in the distance between these spacecraft, changes smaller than the width of an atom LISA, we'll be able to detect the low-frequency gravitational waves generated by truly colossal events, like the merging of supermassive black holes at the centers of galaxies. Each gravitational wave is a fingerprint of the massive objects that created it. By listening to this cosmic symphony, we can pinpoint the locations and masses of the heaviest objects in the galaxy, the ones that carve out the deepest gravitational wells and have the most profound influence on the shape of our interstellar highways. It's like using sonar to map the ocean floor. We send out no pulse, but we listen to the echoes of cosmic collisions to understand the topography of the deep gravitational sea. The sheer volume of data generated by these missions would be incomprehensible to the human mind. We are talking about petabyte upon petabyte of positional data for billions of stars, combined with a continuous stream of gravitational wave signals. This is where artificial intelligence and supercomputing become not just useful but absolutely essential. The task is akin to creating a 3-dimensional topographic map of an entire continent, but without ever setting foot on the ground. You would have satellite images, aerial photographs, and geological survey data, all different types of information that need to be fused together into a single, coherent model. In our case, the satellite images are the astrometric data, the aerial photographs are the gravitational wave signals, and the geological surveys are our existing knowledge of physics. Supercomputers would run complex simulations based on the laws of general relativity, modeling how the gravitational fields of billions of objects interact over millennia. Then machine learning algorithms would be unleashed on this simulated data, learning to recognize the signatures of stable pathways, resonant orbits, and potential hazards. Once trained, these AI cartographers would be set loose on the real data from our telescopes and observatories, cross-referencing, refining, and validating the model, gradually filling in the blank spaces on our galactic map with ever-increasing confidence and detail. They would be the ones to identify the most promising routes for our first interstellar voyages, calculating trajectories that would be impossibly complex for any human team to derive. The success of this monumental mapping effort hinges entirely on our ability to perceive forces that are, by their very nature, almost imperceptible. It is a testament to human ingenuity that we are developing the tools to see the unseen, to hear the silent music of the spheres. This grand cartographic project would be one of the most significant scientific undertakings in history, creating a resource that would benefit not just exploration, but our fundamental understanding of the universe. It would give us a dynamic, living map of the Milky Way, a guide to the currents that flow between the stars, but a map, no matter how detailed, is useless without a skilled navigator who can read it, interpret its symbols, and make decisions in real time. And for a journey lasting centuries, that navigator cannot be human. Even with the most exquisitely detailed map of the galaxy's gravitational highways, a journey between the stars would be impossible without the right kind of pilot. The cold, hard reality of interstellar distances makes human guidance from Earth completely unworkable. Consider a mission to a star just 10 light-years away. If the spacecraft encounters an unexpected obstacle, a dense cloud of dust, a slight shift in a gravitational pathway, and sends a message back to Earth asking for instructions, it would take 10 years for that distress call to arrive. By the time mission controllers on Earth analyzed the problem and sent a solution back, another 10 years would pass. 20 years would have gone by, and the spacecraft, left to its own devices, would have long since met its fate. For journeys that could span centuries, the crew, if there is one, would be generations removed from the original mission planners. The only entity that can possibly captain such a vessel is one that is on board, one that can think, adapt, and make life or death decisions in real time, completely autonomously. That captain is an artificial intelligence. This would not be the simple, rule-based autopilot that keeps a satellite in orbit. This is a system of almost unimaginable sophistication, an AI that serves as the ship's mind, its senses, and its intuition. Its primary function would be continuous, real-time gravitational field analysis. Using a constant stream of data from its sensors, the AI would maintain a dynamic, three-dimensional model of the local space-time geometry around the spacecraft. It would be calculating its position not relative to distant stars, but within the flowing gravitational topography we discussed, identifying the subtle slopes and currents that make up its chosen highway. This is a task of immense computational complexity, requiring the AI to solve the intricate equations of general relativity on the fly, constantly optimizing the spacecraft's trajectory for maximum efficiency and safety. It's the difference between a modern airliner's autopilot, which follows a pre-programmed flight plan, and a master sailor who can feel the wind shifting, see the currents changing, and instinctively adjust the sails to harness every ounce of nature's power. This AI would be that master sailor, but for the cosmos itself. To prepare for this role, the AI wouldn't just be programmed, it would be educated. Long before launch, it would undergo a rigorous training regimen inside hyper-realistic simulations of the galaxy. Using the gravitational maps created by observatories like LISA, scientists would build a digital twin of the Milky Way, a vast, virtual playground where the AI could learn. In this simulator, it would practice navigating between star systems millions of times. It would encounter every conceivable scenario, a stable pathway that suddenly becomes turbulent due to the unseen influence of a dark matter clump, a promising shortcut that leads perilously close to a neutron star's deadly radiation belt, a navigational anomaly caused by a rogue planet drifting through the void. Through a process of machine learning, the AI would learn to recognize the early warning signs of these hazards. It would discover strategies for recovery, learning which course corrections are most effective and which consume too much precious fuel. This training would ingrain a kind of cosmic intuition, an ability to make split-second judgments based on patterns too complex for any human to consciously process. The true test, however, comes when the AI is alone, light years from home, and faces a situation its trainers never anticipated. This is where the AI transitions from a sophisticated tool to a genuine autonomous agent. It must be capable of what engineers call graceful degradation. If a primary sensor fails, it must be able to cross-reference data from other systems to maintain its situational awareness. If it calculates that its current path will lead it into a dangerous region, it must be able to generate and evaluate multiple alternative routes, weighing factors like travel time, fuel consumption, and scientific value. Most critically, it must be able to do all this without ever experiencing the paralysis of indecision. The AI's decision-making architecture would be built around core, unbreakable mission directives principles like preserve the spacecraft, continue the mission, and maximize scientific return. These directives would act as a moral compass, guiding its choices when there are no perfect answers. It becomes more than a navigator. It becomes the guardian of the mission itself, a custodian of humanity's investment and ambition, carrying our hopes across the light years with a cool, calculated intelligence that we have designed but will never directly control. The effectiveness of this brilliant mind, however, is entirely dependent on the quality of the information it receives. This leads us directly to the spacecraft's sensory apparatus, the suite of technologies that will allow it to perceive the invisible forces that guide its way. But a brilliant navigator is only as good as its eyes and ears. For our AI pilot, navigating the invisible highways means perceiving forces that are, by human standards, imperceptible. It cannot look out a window and see the gravitational valleys it needs to traverse. Instead, it relies on a suite of exquisitely sensitive instruments, a sensory system designed to feel the faintest tugs and tremors in the fabric of space-time itself. The most fundamental of these tools would be an accelerometer, but not the kind found in a smartphone. We are talking about a device of almost magical sensitivity. Imagine an instrument so precise it can detect a change in velocity equivalent to a single grain of sand gently nudging a massive ocean liner. This is the level of sensitivity required to map the local gravitational field. As the spacecraft moves through space, it would experience tiny, continuous variations in the pull of gravity. Passing near a concentration of mass, even something as diffuse as a cloud of dark matter, would create a minute acceleration, a slight pull in one direction. The accelerometer would detect this infinitesimal tug, allowing the AI to construct a real-time, three-dimensional picture of the gravitational topography immediately surrounding the vessel. It's akin to a submarine using sonar to map the ocean floor, but instead of sound waves, it uses the force of gravity itself to feel the contours of the unseen landscape. This constant stream of data allows the spacecraft to stay centered in the optimal flow of the highway, making tiny, thruster-fired adjustments to its course, much like a driver makes subtle turns of the steering wheel to stay in their lane. While accelerometers provide a detailed feel for the local road conditions, they don't solve the fundamental problem of deep space navigation, knowing exactly where you are on the map. On Earth, we have the Global Positioning System, a constellation of satellites broadcasting precise timing signals that our devices use to triangulate position. For an interstellar voyage, we need a galactic equivalent. Incredibly, nature has already provided one. Scattered throughout the galaxy are pulsars, rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. Like cosmic lighthouses, these beams sweep across space, and if one of those beams points toward Earth, we see a regular, repeating pulse of energy. The timing of these pulses is astonishingly stable, rivaling the precision of atomic clocks. This makes pulsars perfect celestial beacons. An interstellar spacecraft would carry a dedicated telescope, a pulsar timing array, pointed at a carefully selected set of these spinning stars. By meticulously measuring the arrival time of the pulses from multiple pulsars in different parts of the galaxy, the onboard computer can perform a form of triangulation. Because the position of each pulsar and its pulse frequency are known with extreme accuracy, any slight deviation in the expected arrival time of the pulses tells the AI exactly how far it has drifted from its intended course. It's a self-correcting system that provides a continuous, absolute position fix across the vast, empty gulf between stars. This pulsar-based GPS would be the primary method for keeping the spacecraft on its long-term trajectory, ensuring that after a journey of 100 years, it arrives not just in the general vicinity of a star, but precisely at the gravitational interchange it was aiming for. The future of this sensory technology may lie in the strange and counterintuitive world of quantum mechanics. Researchers are already developing quantum sensors that could revolutionize our ability to measure gravity. These devices exploit the bizarre properties of quantum particles, such as superposition and entanglement. One promising technology is the atom interferometer. In simple terms, this device uses lasers to cool a cloud of atoms to a fraction of a degree above absolute zero, bringing them to a near motionless state. Then it splits the quantum wave of each atom, sending it along two different paths before recombining them. Any tiny difference in the gravitational field experienced along those two paths will cause a detectable shift in the interference pattern when the waves recombine. The sensitivity is staggering. Such a sensor could detect the gravitational influence of a small hill several kilometers away, or the minute gravity of a human being standing next to it. On an interstellar spacecraft, a quantum gravimeter could map the local gravitational landscape with a resolution far beyond what classical accelerometers can achieve, feeling the subtle texture of space-time with a fineness we can barely imagine. It could detect the gravitational wake of a passing asteroid or the faint signature of an undiscovered planet orbiting a distant star, all by feeling the infinitesimal tugs on a cloud of ultra-cold atoms. This would give the AI navigator an almost tactile sense of its environment, allowing it to choose the smoothest and safest path with unparalleled confidence. Together, this suite of sensors, the hypersensitive accelerometer, the pulsar timing array, and the quantum gravimeter, forms the spacecraft's perceptual system. They work in concert, each compensating for the other's limitations. The pulsar array provides the long-range, absolute positioning, the big-picture view from the galactic map. The accelerometers and quantum sensors provide the high-resolution, real-time data on the immediate road conditions, the potholes and curves of the gravitational landscape. This constant, rich stream of data flows into the AI, which integrates it all into a single, dynamic, and ever-evolving model of reality. The AI doesn't just see a dot on a static map, it experiences a flowing, living topography. It can predict how the gravitational currents will shift hours or days in advance, anticipating turbulence and planning evasive maneuvers long before they are needed. This fusion of perception and intelligence is what transforms a simple probe into a true cosmic voyager, an entity capable of reading the hidden roads of the universe. But perceiving the highway with such incredible fidelity is only half the battle. The vessel that carries this sophisticated mind must itself be a masterpiece of engineering, designed not for a violent sprint, but for a patient, graceful journey lasting centuries. This new paradigm of travel demands a completely new kind of spacecraft. Forget the traditional image of a mighty rocket, engines blazing with immense power as it struggles against Earth's gravity. The vessel designed to ride the invisible highways is not a sprinter. It is an ultra-marathon runner built for endurance, grace, and intelligence over raw strength. Its design philosophy flips conventional space engineering on its head. Instead of being a massive fuel tank with a tiny payload attached, this interstellar cruiser is all about the payload. The hull is not shaped for atmospheric re-entry, but for long-term survivability in the deep void, a protective shell housing the most precious cargo, the sophisticated AI brain and its array of hypersensitive sensors. Every system is engineered with one overriding goal: to remain functional not for years, but for centuries, reliably carrying out its mission across generations of travel. The most striking difference lies in the propulsion system. A traditional rocket relies on powerful, continuous thrust to achieve its velocity, carrying mind-boggling amounts of propellant that constitute the vast majority of its launch mass. For our highway traveler, this approach is not just inefficient, it's counterproductive. The primary source of acceleration is not its own engine, but the gravitational currents it navigates. Therefore, its propulsion system is minimalistic and highly efficient, used only for precise course corrections. Think of small, electrically powered ion thrusters or even more advanced plasma drives. These engines provide only a faint, whisper-like thrust, but they can fire continuously for years, even decades, using minuscule amounts of propellant. A tiny nudge at just the right moment, as the spacecraft approaches a Lagrange point interchange, for instance, is all that's needed to shift it from one gravitational pathway to another, setting it on a new course for the next star system. The ship doesn't fight the cosmic currents. It uses its subtle thrusters to steer within them, like a kayaker using gentle paddle strokes to navigate a powerful river. To sustain itself on a voyage that could last 1,000 years, the spacecraft needs a power source as reliable and long-lived as the journey itself. Solar panels, so effective in the inner solar system, become useless as the ship ventures far from the sun's light. The answer likely lies in advanced nuclear power. A compact fission reactor, perhaps using uranium or thorium, could provide a steady, unwavering supply of electricity for centuries. There's even the tantalizing possibility of fusion reactors, mimicking the power source of the stars themselves, offering even greater energy density. This nuclear heart would power everything: the AI's constant computations, the sensor arrays scanning the darkness, the communication system sending intermittent reports back to Earth, and those delicate course correction thrusters. In some concepts, the power source and propulsion system could be one and the same. An idea that has captivated scientists for decades is the nuclear pulse propulsion, though for our low-energy trajectory craft, a more elegant solution might be a massive light sail. Think of a sailboat, but instead of catching wind, it's pushed by the physical pressure of photons streaming from a star or even a powerful Earth-based laser array. This provides acceleration without any propellant at all, a perfect complement to the fuel-free nature of gravitational sailing. But a reliable power source is meaningless if the spacecraft's delicate internal systems are fried by radiation long before reaching its destination. The interstellar medium is filled with high-energy cosmic rays, and passing near certain celestial objects can bring intense radiation showers. Therefore, the spacecraft's hull must be a fortress against this invisible bombardment. This wouldn't be simple aluminum plating. We're talking about advanced composite materials, layers of hydrogen-rich plastics, or even water ice stored within the walls, as hydrogen is exceptionally good at blocking cosmic radiation. The ship might have a dedicated storm shelter at its core, a heavily shielded vault where sensitive electronics are housed, protecting them during periods of unusually high radiation. This isn't just about protecting silicon chips. If the mission carries biological payload seeds, bacterial cultures, or frozen embryos, this shielding becomes the wall that separates life from oblivion. The entire vessel is, in essence, a time capsule, designed to preserve its precious contents against the relentless decay of the cosmic environment for time spans that dwarf recorded human history. This radical shift in design from a powerful rocket to an intelligent, enduring sailboat fundamentally changes the economics and feasibility of interstellar travel. It suggests that the first craft to journey to the stars might not be gargantuan world ships, but smaller, more focused probes. They would be robotic scouts, the equivalent of the caravels that first mapped the coastlines of new continents. Their mission is not a desperate sprint for survival, but a patient, systematic survey of the galactic highway network. They are the Pathfinders, proving the routes so that larger, more ambitious vessels can follow. Yet, for all its sophisticated design and robust shielding, this pioneering vessel is embarking into a realm of profound and unknown danger. The cosmic highways may be efficient, but they are far from safe. The very forces that create these pathways also concentrate the hazards of the galaxy, presenting challenges that will test the limits of the AI's ingenuity and the spacecraft's durability at every light year of its epic journey. Yet for all its graceful design and brilliant navigation, the journey along these cosmic highways is far from a peaceful cruise. The very forces that create these efficient pathways also tend to concentrate the dangers of the galaxy, turning the smoothest-looking routes into potential obstacle courses. The first and perhaps most insidious threat comes from the smallest objects, micrometeoroids. These are not just random specks of dust floating in the void. In the regions of space where gravitational forces are perfectly balanced, like the stable Lagrange points we discussed, something counterintuitive happens. These areas can act as cosmic collection points, gently gathering dust and small debris over millions of years. A highway interchange that promises a free gravitational boost might also be a subtle trap, filled with a diffuse cloud of hypervelocity particles. A spacecraft traveling at even a fraction of light speed would collide with these tiny objects with the energy of a cannon shot. A single grain of sand could puncture shielding, damage critical sensors, or decompress a habitation module. The danger is amplified because this debris is often invisible to telescopes. It's too small to see from Earth, but large enough to be catastrophic. The AI navigator would need to rely on predictive models, using its knowledge of gravitational dynamics to identify which pathways are likely to be the cleanest, avoiding the ancient debris fields that accumulate at otherwise attractive gravitational waypoints. An even more dramatic peril awaits near the most extreme objects in the galaxy. While our spacecraft is designed to use gravity, there is a threshold where that gentle slope becomes a deadly cliff. Consider a binary star system where two stars orbit each other in a complex, often chaotic dance. Their overlapping gravitational fields create a turbulent and rapidly changing landscape. A pathway that seems stable one moment could vanish the next as the stars shift position. But the greater danger is tidal force. This is the difference in gravitational pull across an object. If you were to fall feet first into a black hole, the gravity at your feet would be so much stronger than at your head that your body would be stretched into a long, thin strand, a process picturesquely called spaghettification. Now imagine a spacecraft passing too close to a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. The tidal forces there would be immense. Even from a safe distance, the difference in gravity between the side of the ship facing the star and the side facing away could be enough to wrench the vessel apart, tearing metal alloys as if they were tissue paper. The AI's models would need to calculate strict exclusion zones around such objects, plotting trajectories that keep a respectful and safe distance from these gravitational monsters. Beyond the crushing force of gravity lies an invisible, penetrating danger: radiation. The galaxy is filled with high-energy particles, but certain locations act as natural accelerators, creating zones of intense radiation that would be instantly lethal to any life and destructive to electronics. Pulsars, those useful cosmic lighthouses for navigation, are also furious generators of radiation, blasting their surroundings with powerful beams of X-rays and gamma rays. Similarly, the accretion disks around black holes, where matter spirals inward at nearly the speed of light, glow with incredibly intense radiation. Flying through such a region would be like sailing a wooden ship through a nuclear firestorm. The spacecraft's advanced shielding would be put to the ultimate test. However, shielding is heavy, and there's a limit to how much protection can be practically carried. The smarter solution, once again, lies in avoidance. The AI would continuously monitor its environment for radiation signatures, its sensors acting as a kind of cosmic weather forecast. Long before the ship enters a dangerous zone, the AI would detect the rising levels of high-energy particles and calculate a new route, steering the vessel around the stellar equivalent of a hurricane, even if it adds years to the journey. This constant dance with danger highlights the true genius of the autonomous AI navigator. Its role is not just to follow a pre-planned map, but to be a dynamic pathfinder in real time. The gravitational map of the galaxy it launched with would be a best guess, a snapshot in time. Over a century-long journey, star systems move, new objects can drift into the path, and unforeseen events like a supernova could drastically alter the local space-time geometry. The AI must therefore be capable of continuous reconnaissance. It would use its sensor suite to constantly update its internal map, comparing what it expected to find with what it actually detects. If it encounters an unexpected gravitational anomaly, perhaps a previously unknown dwarf planet or a dense knot of dark matter, it doesn't panic, it recalculates. It runs millions of simulations in seconds, evaluating alternative pathways, weighing the risks of each new route against the hazards of the original plan. It might identify a safer, parallel path just a few million kilometers off the original course, a gravitational side road that bypasses the danger entirely. This ability to adapt and reroute autonomously is what separates a successful multi-generational voyage from a tragic disappearance into the void. Surviving these myriad dangers is a monumental achievement in itself, but it forces us to reconsider the very objective of such an epic undertaking. Is the goal simply to survive the journey and reach a single, pre-selected point of light? Or does the existence of this network of pathways suggest a more profound and ambitious mission? This fundamental shift in the very purpose of an interstellar mission might be the most transformative aspect of the invisible highway concept. For centuries, our vision of traveling to the stars has been fixated on the destination. We pick a single, tantalizing point of light, Proxima Centauri, Tau Ceti, TRAPPIST-1, and we pour all our energy, all our engineering, into the monumental challenge of reaching that one specific place. The entire mission becomes a high-stakes gamble, a desperate sprint across the void where failure to reach that single target means total mission failure. It's a paradigm born from the limitations of propulsion, where the immense energy cost forces us to bet everything on one roll of the dice. But what if we're thinking about it all wrong? The existence of a networked system of gravitational pathways changes the game entirely. Instead of a single destination, the destination becomes the network itself. Imagine not launching a probe to a star, but launching an explorer onto a highway. Its primary mission objective is no longer to arrive at a specific exit ramp, but to travel the highway system, studying every interchange, every rest stop, and every interesting feature along the way. This spacecraft would be programmed with a flexible, branching mission plan. Its AI navigator would have a primary goal: to maximize scientific return by efficiently traveling from one gravitational node to the next. The first target might be a nearby node within our own solar system's extended gravitational influence, perhaps a stable point influenced by the combined pull of the Sun and the hypothetical planet 9. From there, the AI would analyze the outbound pathways, selecting the most promising one that leads to the next interesting feature, maybe a rogue planet drifting between the stars or a diffuse molecular cloud. Each leg of the journey becomes a discrete, valuable scientific expedition in its own right. This approach transforms the nature of a multi-generational voyage from a grim endurance test into a continuous, rolling discovery. On a traditional generation ship aimed at a single star, the centuries in between are a terrifying void, a long, dark waiting period where the sole purpose is survival. The crew or their descendants live for a goal they may never see, their lives defined by the anticipation of arrival. But on a network exploration vessel, the journey is the purpose. Every few decades or even years, the ship arrives at a new node, a new system to study. It might swing through a binary star system, spending 5 years mapping its planets and analyzing their atmospheres. Then, it uses the gravitational dynamics of that system to slingshot towards a nearby neutron star, where it can conduct unique astrophysical experiments impossible anywhere else. The mission is a continuous process of engagement with the galaxy, a perpetual state of arrival and discovery. The crew, whether awake or in suspended animation, would experience a life of constant exploration, not interminable waiting. This reframes the entire psychological and sociological challenge of a generation ship, turning it from a floating ark into a mobile research institute, a university that travels the cosmos. The scientific value of this approach is immeasurably greater. A single mission to one star system provides one data point. A network exploration mission provides dozens or even hundreds. We could move from studying a single example of an exoplanet to conducting the first ever comparative planetology on a galactic scale. How common are Earth-like planets around G-type stars? What about around red dwarfs? By visiting multiple systems of each type, we could begin to understand the rules of planetary formation. We could search for biosignatures not in one place, but in many, dramatically increasing our chances of finding evidence of life or even understanding the conditions that make it possible. Furthermore, the spacecraft itself becomes a unique observatory. As it travels along these pathways, its changing vantage point would allow it to create a stereo map of the galaxy, measuring the distances to stars with unprecedented accuracy and studying cosmic phenomena from angles impossible to achieve from our static position around the Sun. This shift also introduces a powerful element of redundancy and resilience. In the old point-to-point model, if the target star system turns out to be a disappointment, perhaps its promising planets are barren or it possesses some unforeseen danger, the entire mission is a failure. On a network exploration, if one node is a dead end, it's merely a minor setback. The AI simply recalculates, selects the next most promising pathway from its current location, and continues the mission. The value of the journey is not lost. This flexibility makes the entire endeavor more robust and far more likely to yield a positive return on the colossal investment. It acknowledges the fundamental truth of exploration. We cannot know what is out there until we look. Instead of betting everything on a single guess, we empower our robotic ambassador to adapt, to explore, and to follow the data wherever it leads. This vision of a patient, systematic survey of our galactic neighborhood feels less like a desperate gamble and more like the logical, mature next step in humanity's journey of discovery. It's a paradigm that makes the grand dream of interstellar travel feel not only more achievable but infinitely more purposeful. Before we commit to a voyage spanning light years, we must first prove that we can reliably navigate the cosmic currents right here in our own celestial backyard. The grand vision of interstellar highways depends on a series of humble, near-future Pathfinder missions, small, intelligent probes designed to test every aspect of this revolutionary technology within the familiar confines of our solar system. Think of these not as final products, but as the prototypes, the experimental vehicles that will work out the inevitable kinks and surprises before we risk a mission of interstellar magnitude. The first logical step would be to send a fleet of small, cost-effective probes on increasingly complex shakedown cruises, starting with the most accessible gravitational features we know, the Lagrange points of the Earth-Moon system. Imagine a mission involving a pair of suitcase-sized satellites launched together into a high Earth orbit. Their first objective would be to demonstrate autonomous rendezvous and station keeping at the Earth-Moon L1 point, that delicate balancing point between our planet and its moon. But they wouldn't just park there. Their true test would be to use their onboard AI and miniature ion thrusters to navigate the stable and unstable manifolds, the gravitational inflow and outflow pathways that connect to this point. One probe might demonstrate an inbound trajectory, using a tiny burst of thrust to insert itself onto the natural pathway flowing toward L1, arriving with remarkable fuel efficiency. The other could then execute an outbound maneuver, catching the gravitational current flowing away from L1 and riding it toward a lunar flyby or even a transfer to the distant Earth-Moon L2 point. The entire mission would be a ballet of autonomous decision-making, with the probe's AI brains constantly comparing their sensed accelerations and positions against pre-loaded gravitational maps, making minute corrections to stay perfectly on course. Success here would validate the core principle that we can indeed program a machine to feel and ride these subtle gravitational pathways. Having mastered the local dynamics of the Earth-Moon system, the next step is to scale up the challenge. A follow-on mission would target the Sun-Earth Lagrange points, a much more complex environment dominated by the Sun's immense gravity. A single probe could be sent on a grand tour of these celestial interchanges. It might start by entering a halo orbit around the Sun-Earth L1 point, the ideal location for monitoring solar activity. After a period of observation, its AI navigator would calculate the perfect moment to fire its thrusters, kicking itself onto a pathway leading to the Sun-Earth L2 point, the stable region behind Earth where the James Webb Space Telescope resides. This journey between solar Lagrange points is far more demanding than the Earth-Moon trip, requiring exquisite precision to navigate the combined gravitational fields of the Sun and Earth. The probe's sensors would be pushed to their limits, tasked with distinguishing the subtle tugs of solar radiation pressure from the true gravitational gradients it needs to map. This mission would serve as the ultimate test for the AI's trajectory optimization algorithms in a multi-body environment, a critical dress rehearsal for the kind of navigation required between stars. The final and most ambitious Pathfinder within our solar system would be a mission to the realm of the giants, the Sun-Jupiter Lagrange points. Jupiter, with its staggering mass, creates the deepest gravitational well in the solar system after the Sun itself. Its Lagrange points, particularly the stable L4 and L5 points leading and trailing its orbit, are not mere mathematical points but vast, stable regions home to the Trojan asteroids. Sending a probe to this distant outpost, over 5 times farther from the Sun than Earth presents a monumental challenge. The communication delay alone would be close to an hour each way, making real-time control from Earth impossible and forcing total reliance on the probe's autonomous systems. The gravitational landscape there is incredibly complex, perturbed by Jupiter's large moons and the presence of thousands of Trojan asteroids. The probe's mission would be to autonomously navigate this cluttered, dynamic environment, perhaps even performing a close flyby of a Trojan asteroid. It would need to identify potential hazards, recalculate its path on the fly, and continuously update its internal model of the local gravitational field. Successfully operating in this extreme environment would be the definitive proof that our AI and sensor technology is mature enough to handle the unpredictable conditions of interstellar space. These Pathfinder missions are about more than just technology demonstration. They are about building confidence. Each successful mission, from the simple Earth-Moon test to the complex Jupiter-Trojan tour, would provide a crucial data point, validating our models and proving the reliability of our systems. They allow engineers to encounter and solve problems close to home, where help or a backup mission is still feasible. A failure in the Earth-Moon system is a setback. A failure on an interstellar mission is a total loss. By methodically proving the concept step by step, we de-risk the entire endeavor, transforming interstellar travel from a leap of faith into a logical, incremental engineering program. The data these Pathfinders collect would be invaluable, refining our gravitational maps of the solar system and providing real-world experience that would inform the design of the first true interstellar voyages. This gradual, proven approach is what separates a sustainable spacefaring future from mere science fiction, laying the concrete foundation upon which the dream of the stars will finally be built. While the dream of sailing the cosmic currents is fueled by a profound human desire to explore, the colossal investment required to build this capability demands a powerful, tangible incentive. The vision of invisible highways is not just a scientific marvel, it is an economic inevitability driven by forces far more pragmatic than wanderlust. The development of this technology will be accelerated by the oldest motivation in human history, the pursuit of resources and economic advantage. The key to unlocking the solar system's vast wealth lies not in building bigger rockets, but in mastering the art of low-cost transportation. Imagine the economic potential of asteroid mining. We know that a single metallic asteroid, just a few hundred meters across, can contain more platinum, gold, and rare earth metals than have been mined in all of human history. The problem has never been the existence of these resources, but the astronomical cost of reaching them, retrieving them, and bringing them back to where they are needed. This is where the invisible highways change everything. By utilizing the interplanetary transport network, a mining spacecraft would require a fraction of the propellant needed for a conventional mission. It could hitch a ride on a gravitational current to a resource-rich asteroid belt, perform its extraction, and then catch a return current back to Earth orbit or a processing facility at a Lagrange point. This dramatic reduction in fuel cost transforms asteroid mining from a fantastically expensive stunt into a viable, profitable industry. It would enable the large-scale extraction of materials essential for advanced electronics, clean energy technologies, and construction in space itself, creating a self-sustaining economic loop that funds further expansion. This new resource economy will require infrastructure, and that infrastructure will naturally coalesce around the most strategically valuable locations, the gravitational nodes themselves. Think of a Lagrange point not as an abstract point in space, but as the future equivalent of a deep water port like Singapore or the Suez Canal. These are the natural hubs where gravitational currents converge and diverge. A spacecraft arriving from the asteroid belts with a cargo of raw metals could efficiently rendezvous at, say, the Earth-Moon L1 point. There, a processing station could refine the ore. Another vessel, arriving from a manufacturing facility in lunar orbit with a load of finished components, could meet it. They would exchange cargo, and each would then catch an outbound pathway to their next destination. These Lagrange points become the intermodal shipping terminals of the solar system, the places where cargo is transferred and routes are changed. The strategic importance of controlling such a node cannot be overstated. The nation or corporation that establishes a permanent presence at a key Lagrange point would effectively control a toll gate on a major interplanetary trade route. This isn't about planting a flag for prestige. It's about securing a pivotal choke point for future commerce, much like historic control of strategic straits and canals translated into immense economic and political power on Earth. Therefore, framing the development of cosmic highway technology as a mere expense is a profound mischaracterization. It is, in fact, one of the most strategic investments humanity could make. It is an investment in securing our long-term economic and territorial expansion beyond the confines of our single, vulnerable planet. The initial costs of developing the AI, the sensors, and the Pathfinder missions are the seed capital for an enterprise that will ultimately pay exponential dividends. The economic activity generated from mining and manufacturing to transportation and tourism would create a space-based economy that dwarfs anything we have on Earth today. This isn't a cost, it's the foundation of a post-scarcity future where the limitations of Earth's finite resources are lifted and human civilization can grow in ways we can barely imagine. This powerful economic rationale provides a concrete, compelling reason for governments and private enterprises to collaborate on what might otherwise seem like a purely scientific endeavor. The promise of unimaginable wealth and strategic advantage will ensure that the political will and the capital necessary for this project will eventually materialize. This economic engine suggests a future where the invisible highways are not lonely paths for a few brave probes, but bustling, well-traveled corridors, humming with the traffic of cargo haulers, passenger liners, and construction vessels. But this vision of a busy interplanetary economy immediately raises a complex and critical question. In the absence of earthly laws, who will build the traffic lights, set the speed limits, and prevent cosmic gridlock on these celestial freeways? As this network of cosmic highways begins to see traffic, a pressing question emerges from the realm of physics and engineering into the complex world of human affairs. Who exactly is in charge? We are envisioning a future where the most strategically valuable real estate is not on any planet, but at precise points in the void, the Lagrange points and the gravitational pathways connecting them. The fundamental issue is one of ownership and access. Can a nation or a private company plant a flag at the Sun-Earth L1 point and declare it sovereign territory, controlling all traffic that passes through this natural celestial interchange? Or are these pathways, which were formed by the fundamental laws of the universe long before humanity existed, the common heritage of all humankind, to be managed for the benefit of everyone? This is not a trivial debate. The outcome will set the stage for either a future of cooperative exploration or one of potential conflict in the high frontier. We have historical precedents for this very dilemma right here on Earth. Consider the law of the sea. For centuries, nations claimed territorial waters extending just a short distance from their shores. Beyond that lay the high seas, a global commons where ships of all flags could travel freely. This principle of freedom of navigation was essential for fostering international trade and exploration. Similarly, international airspace is governed by treaties that allow civilian aircraft to overfly countries without seeking individual permission. The cosmos demands a similar but far more sophisticated framework. We will need a new set of laws, a kind of space traffic control for the gravitational age. This wouldn't be about restricting access, but about ensuring safety and preventing catastrophic accidents. Just as maritime law has rules for right-of-way to prevent collisions between massive container ships, we will need protocols for spacecraft navigating the intricate approaches to a busy Lagrange point. What happens when a slow-moving, multi-generational colony ship on a fixed low-energy trajectory has its path intersected by a faster, AI-piloted probe making a course correction? Which vessel has priority? Establishing these rules of the road before traffic gets heavy is not just prudent, it is essential for survival. The ethical considerations extend far beyond simple traffic management and into profoundly unsettling territory. We are discussing sending highly advanced artificial intelligence systems on voyages that could last for millennia. These AI entities would be endowed with immense responsibility. The safety of any crew or cargo, the success of a mission representing a colossal investment of resources and hope, and the power to make life or death decisions in complete isolation. What are our ethical obligations to these sentient creations? Are they merely sophisticated tools, disposable upon mission completion? Or do they attain a certain status as the long-term guardians of humanity's legacy? Furthermore, consider the potential for these autonomous systems to encounter the unimaginable. What if a probe arrives at a distant star and finds evidence of a simple, non-intelligent extraterrestrial life form? Does its programming allow it to conduct experiments that might harm that ecosystem? The instructions we embed in these AI minds today could have consequences echoing for millions of years, long after our civilization is dust. We are, in effect, creating digital ambassadors that will represent humanity to the cosmos for better or worse. Their actions, guided by the ethical frameworks we instill in them, will define our species' character in the galactic community. This intertwining of technological ambition and profound responsibility highlights a crucial truth. The challenge of building the interstellar highways is only half the battle. The other, equally daunting half is building the social, political, and ethical frameworks to use them wisely. It demands a level of global cooperation that has often eluded us here on Earth. The project is too vast, the stakes too high for any single entity to manage alone. This necessitates a collaborative spirit reminiscent of the International Space Station, but on a planetary scale, involving every spacefaring nation and corporation. Forging these treaties and ethical guidelines will be messy and difficult, a testament to the fact that our greatest obstacle to reaching the stars may not be the void of space, but the complexities of our own nature. Successfully navigating this socio-political challenge is the final prerequisite. the crucial step that transforms the dream from a technical possibility into a sustainable reality for all of humanity. With the cosmic highways mapped and the technology proven, we can finally envision the pioneers who will first set sail upon them. The nature of these first interstellar voyages will likely fall into two distinct, yet equally revolutionary categories, each representing a different philosophy for spreading life beyond our solar system. The first is the robotic seed ship, a mission of profound patience and technological foresight. Imagine a vessel no larger than a shipping container, launched from a Lagrange point gateway with just enough thrust to enter the flow of the interstellar network. For centuries, this silent craft would coast along its predetermined gravitational pathway, its AI mind in a low power state, its sensitive instruments dormant, a cosmic sleeper ship. Its journey is one of pure potential, a message in a bottle cast into the galactic currents. Upon finally arriving at its destination, perhaps a stable Lagrange point in a nearby star system like Alpha Centauri, or even orbiting a potentially habitable exoplanet, it would awaken. Its first act would not be to send a message home, which would take years to arrive, but to begin its primary mission, construction. Using advanced manufacturing systems, like 3D printers that fabricate structures from local asteroid dust or pre-packaged materials, the seed ship would tirelessly build the infrastructure for those who will follow. It might assemble a communication laser powerful enough to reliably send data back to Earth, construct a basic landing pad, or even deploy a network of smaller survey probes to map the entire star system. This robotic vanguard does not carry life. It prepares the ground for it, acting as an automated advance team that transforms an unknown destination into a prepared site, all before any human ever sets out on the journey. In stark contrast to the minimalist seed ship stands the generation ship, a concept that is less a spacecraft and more a moving piece of human civilization. This would be the largest and most complex structure ever built by humanity, a self-contained world designed to sustain a population of thousands for a voyage lasting several centuries. Picture a massive rotating cylinder or a series of interconnected rings, creating artificial gravity through centrifugal force. Inside, you would find not sterile corridors, but a rich, Earth-like environment. Parks, farms, bodies of water, and entire towns. The inhabitants of this vessel would not be astronauts in the traditional sense. They would be citizens born, living, and dying aboard the ship. For them, the journey is not an interval to be endured but life itself. Their society would evolve independently, developing its own culture, traditions, and even language, all while slowly cruising along the invisible highway at a fraction of the speed of light. The goal of the generation ship is not merely to deliver humans to a new world, but to deliver a fully functional, thriving society, one that arrives ready to colonize rather than just visit. It is a hedge against existential risk for humanity, ensuring that even if disaster befalls Earth, our species continues among the stars. The choice between these two models involves a fundamental trade-off between risk and reward. The robotic seed ship is by far the safer and more economical option. It requires no life support, no social engineering, and poses no direct risk to human life. We could launch dozens of these probes to different target systems for a fraction of the cost of a single generation ship, dramatically increasing our chances of success somewhere. However, its payoff is delayed and impersonal. Success would be a silent, automated outpost waiting in the dark, its benefits reaped by generations far in the future. The generation ship, on the other hand, carries immense risk. It is a breathtakingly complex biological and sociological system that must remain perfectly balanced for centuries. A single failure in its closed-loop ecosystem, a social collapse among its crew, or an encounter with an unforeseen hazard could doom everyone on board. Yet its reward is equally profound: the direct, continuous expansion of human presence into the galaxy. It represents a commitment to becoming an interstellar species, not just in theory, but in living, breathing reality. Crucially, the existence of the gravitational highway system is what makes both scenarios significantly more feasible than they would be with conventional propulsion. For the seed ship, the low-energy trajectory means it does not need to carry massive fuel reserves for deceleration upon arrival. It can coast to a gentle stop using the gravitational dynamics of the target system itself, saving enormous mass that can instead be dedicated to its construction and manufacturing systems. For the generation ship, the reduction in propulsion requirements is even more critical. The sheer mass of a world ship is so colossal that accelerating it to even a few % of light speed with rockets is practically impossible. But by using the highways, the ship needs only modest thrusters for course corrections, not primary acceleration. This allows the design to focus on what matters most, creating a sustainable and healthy long-term environment for its inhabitants, rather than being dominated by the engineering of a gargantuan propulsion system. The highways don't make the journeys short, but they make them possible, turning multi-hundred-year voyages from an insurmountable energy challenge into a manageable problem of endurance and social stability. These two visions of our interstellar future, the patient, robotic gardener and the vibrant, traveling ark, make the grand theory of cosmic navigation feel thrillingly tangible. They show us that the path to the stars is not a single, desperate leap, but a spectrum of possibilities we can choose from, each adapted to our courage, our resources, and our vision for humanity's place in the cosmos. While the vision of interstellar highways feels like a concept from the far future, the blueprint is being drafted in laboratories and mission control centers around the world at this very moment. The theoretical foundations are being stress-tested, and the first practical steps are being taken by a dynamic coalition of government space agencies, academic pioneers, and visionary private organizations. This isn't just speculative daydreaming. It's a concerted, global effort to turn physics into a practical roadmap for humanity's expansion. At the forefront of this endeavor are the established space agencies, whose long-term planning is essential for such a monumental project. Within NASA, the NASA Innovative Advanced Concepts Program, or NIAC, acts as a seed fund for ideas that sound like science fiction but are grounded in real science. NIAC has been a critical incubator for technologies relevant to our invisible highways. It has funded early-stage studies into everything from solar sails that could propel probes along these trajectories to advanced propulsion concepts that could one day complement them. Similarly, the European Space Agency has deep expertise in the practical application of these principles, particularly through its extensive work with libration point orbits. Missions like their upcoming Ariel Space Telescope, which will study exoplanet atmospheres from a stable orbit around the Sun-Earth L2 point, are not just scientific endeavors. They are live-fire exercises in the precise navigation and station-keeping required to operate at these gravitational interchanges. Every successful mission to a Lagrange point refines our models and gives engineers more confidence in plotting increasingly complex paths through the solar system's gravitational terrain. Beyond government agencies, the academic world is the engine of fundamental research, where the complex mathematics of chaos theory and celestial mechanics are decoded. Universities like Purdue, with its rich history in astronautics, and the University of Colorado Boulder are hubs for this work. Here, researchers are running incredibly detailed supercomputer simulations of the interplanetary transport network, modeling the flow of spacecraft not just between Earth and Jupiter, but on hypothetical paths through the entire solar system and beyond. Their research papers, with titles delving into invariant manifolds and weak stability boundaries, may seem esoteric, but they are literally writing the mathematical guidebook for future navigators. This is where the grand, conceptual idea of a galactic highway is broken down into precise, calculable trajectories, identifying the specific routes that would require the absolute minimum energy expenditure. This academic research provides the essential theoretical backbone that informs the mission planners at NASA and ESA. Adding a powerful new dimension to this effort are private organizations driven by long-term vision rather than quarterly earnings. The most prominent example is the breakthrough initiatives funded by entrepreneurs like Yuri Milner. While their most famous project, Breakthrough Starshot, aims to send tiny, laser-propelled probes to Alpha Centauri at a significant fraction of light speed, their very existence signals a profound shift. They are asking the big questions about interstellar travel and funding serious scientific and technical studies to find answers. This private investment accelerates the entire field, fostering a competitive yet collaborative spirit that pushes the boundaries of what's considered possible. They are helping to legitimize interstellar studies as a serious field of engineering, not just a fringe academic pursuit. The proof of this accelerating progress is found in specific, groundbreaking research projects. Consider the work on autonomous navigation using pulsar timing. Teams at NASA's Goddard Space Flight Center have already successfully demonstrated a technology called the Station Explorer for X-ray timing and navigation technology, or sextant. This experiment, hosted on the International Space Station, used the incredibly regular X-ray pulses from millisecond pulsars to determine the station's position in space with an accuracy comparable to our terrestrial GPS system. It was a stunning proof of concept, showing that a spacecraft could indeed triangulate its location anywhere in the solar system, or beyond, using these natural cosmic lighthouses, a foundational technology for any interstellar highway traveler. Simultaneously, the data from the Gaia Space Observatory is providing the raw material for our future galactic map. Gaia is meticulously charting the position, distance, and motion of over 1 billion stars in our galaxy. This colossal dataset is not just for creating pretty star charts. It is allowing astrophysicists to weigh the Milky Way, map its dark matter distribution, and understand the gravitational tides that shape the orbits of its stars. Each data release from Gaia adds another layer of detail to our understanding of the galaxy's gravitational potential, the very landscape through which our invisible highways will run. This work, happening right now, is the first step in the multi-generational cartography project that will one day guide our ships. The collaboration between these groups is what makes this moment so exciting. A university team might develop a new navigation algorithm, which is then tested using data from a NASA mission, with funding partially contributed by a private foundation. This synergy is creating a virtuous cycle of innovation. The pace is undeniably accelerating, moving the concept of interstellar highways from the pages of theoretical physics journals into the realm of credible engineering roadmaps. The foundation is no longer just being imagined. It is being calculated, simulated, and tested, piece by intricate piece, bringing the dream of cosmic sailing closer to reality with every passing year. So far, our journey has been guided by the invisible hand of gravity, the master architect of the cosmic highways. But what if gravity is just the first chapter in the manual for interstellar travel? The universe is a symphony of forces, and a truly advanced spacefaring civilization would learn to listen to every instrument in the cosmic orchestra. The next evolutionary step in navigation involves expanding our senses beyond gravity, weaving other fundamental forces of nature into a richer, more robust, and multi-layered navigational web. Imagine our spacecraft's AI not just as a gravitational cartographer, but as a master of cosmic weather, able to read solar winds, magnetic fields, and perhaps one day, even the most enigmatic force in the universe. Consider the humble compass, a tool that has guided explorers for centuries by aligning with Earth's magnetic field. Now, scale that idea up to a galactic level. Our galaxy is filled with powerful magnetic fields, and some of the most intense are generated by pulsars, those rapidly spinning neutron stars we already use as timing beacons. A pulsar's magnetic field is almost unimaginably strong, trillions of times more powerful than Earth's. This field does not just sit there, it rotates with the star, whipping charged particles into a frenzy and creating a vast dynamic structure known as a magnetosphere that can extend light years into space. For a future spacecraft, this could be more than just a navigational hazard to avoid. By carrying sophisticated magnetometers, our vessel could detect the subtle contours of these immense magnetic structures. The AI could use them as secondary road signs, confirming its position triangulated by pulsar timing. In a dense star cluster where gravitational signals might become muddled, the unique magnetic fingerprint of a nearby pulsar could provide a crucial, unambiguous position fix. Furthermore, for a spacecraft equipped with a magnetic sail, a large, superconducting loop that generates its own field to push against a stellar or planetary magnetosphere, these magnetic fields could become a source of propulsion. It would be like a sailor using not just the ocean currents, but also the prevailing winds, harnessing a second, complementary force to gain even greater control and efficiency on their journey. Beyond magnetic fields, there is the constant, gentle pressure of starlight itself. We are all familiar with the concept of solar sails, which use the physical push of photons from a star to accelerate a spacecraft. This technology is already being tested in Earth orbit, but the principle extends to a broader phenomenon, stellar wind. Stars like our Sun constantly emit a stream of charged particles, a plasma, that flows outward, creating a bubble known as the heliosphere. This solar wind exerts a continuous, albeit faint, pressure. For an interstellar traveler, the wind from a star could serve as a persistent navigational cue. As a spacecraft approaches a new star system, its sensors would detect a gradual increase in the density and pressure of this particle wind. The direction of the flow would always point directly back to the star, acting as a kind of cosmic weather vane. By analyzing the composition and intensity of the wind, the AI could infer properties of the star long before it is visually resolved, much like a sailor can smell land on the breeze before it appears on the horizon. This information could be vital for making early course corrections, especially if the goal is to use that same star's light for a final braking maneuver with a light sail. The spacecraft would be navigating not just by the gravity well of the star, but by the very atmosphere it breathes into space. Looking even further into the future, we must consider the most mysterious force in the cosmos, dark energy. This is the name we give to the unknown phenomenon causing the expansion of the universe to accelerate. Its nature is one of the greatest puzzles in physics, but if we could ever understand and measure it locally, it could revolutionize navigation on the grandest scales. Dark energy appears to be a property of space itself, a kind of negative pressure that is uniform throughout the vacuum. If future technology allowed us to build a sensor capable of detecting infinitesimal variations in this dark energy field, perhaps caused by the presence of immense mass concentrations like galaxy clusters, it could provide a truly universal reference frame. While gravity tells us about the topography of space-time, a dark energy sensor could tell us about the fundamental energy density of the void. It would be the ultimate background map against which all other motions could be measured with unprecedented accuracy. This is, of course, highly speculative, but it illustrates a crucial point. The maturity of an interstellar civilization may be measured by the number of cosmic forces it has learned to harness. The first sailors used the wind and currents. We are learning to use gravity. Our descendants might add magnetic fields, stellar winds, and perhaps even the fabric of dark energy itself to their navigational toolkit. This vision points toward a future where space travel is not a battle against the elements, but a graceful integration into the cosmic ecosystem. A mature interstellar vessel would not rely on a single system. Its AI would be a master synthesizer, continuously integrating data from a dozen different sources. It would feel the gravitational slope of a Lagrange point, sense the magnetic signature of a passing pulsar, read the pressure of the local stellar wind, and keep its position fixed against the background hum of dark energy. This multi-layered awareness would provide incredible redundancy and resilience. If one system failed, if, for example, a key pulsar used for timing suddenly went quiet, the AI could seamlessly switch to a navigation mode based on gravitational landmarks and stellar wind patterns. This is the difference between a pilot flying a small plane on a clear day using only visual cues and the captain of a modern ocean liner navigating through a thick fog using GPS, radar, sonar, and inertial guidance systems all at once. The latter has a depth of perception that makes travel safer, more reliable, and more efficient in all conditions. By learning to read the full spectrum of the cosmos, we transform our spacecraft from simple travelers into conscious participants in the dynamic flow of the galaxy, truly sailing with the universe rather than merely through it. Picture a future not a century from now, but a full millennium into our journey, where the very concept of interstellar travel has undergone a revolution as profound as the shift from horse-drawn carriages to global air travel. The Milky Way, which for all of human history has been a breathtaking but untouchable panorama, has become a familiar neighborhood. The invisible highways, once a theoretical marvel, are now as well charted as the transcontinental railways or the major shipping lanes of Earth's oceans. This is no longer the domain of a few intrepid, one-way pioneers. This is the backbone of a functioning interstellar civilization. The galaxy transforms from a gallery of distant, isolated points of light into a single, interconnected community, a network of hundreds, perhaps thousands, of star systems linked by the graceful, energy-efficient flow of traffic along these gravitational pathways. This connectivity would fundamentally reshape human existence. The most immediate and profound change would be the death of isolation. Imagine a research team on a world orbiting a red dwarf star, studying a unique geological formation. Instead of waiting decades for a data packet to be exchanged with Earth, they could dispatch a physical sample to a major research hub at a central Lagrange point, where it would be analyzed by specialists from a dozen different star systems. Scientific discovery would accelerate at an unimaginable pace. A nova observed in one sector of the galaxy could be studied by probes dispatched from multiple directions within a human lifetime, providing a three-dimensional understanding of the event. Breakthroughs in physics, medicine, and engineering would no longer be confined to their world of origin. They would ripple across the network, with knowledge being tested, refined, and built upon by minds that have evolved under different suns, leading to an intellectual renaissance on a galactic scale. The exchange would extend far beyond pure science into the rich tapestry of culture and biology. Art, music, and literature born under the double suns of a binary system would find audiences on worlds with perpetual twilight or in the vast orbital habitats circling gas giants. Philosophical ideas developed by societies that have lived for generations aboard traveling generation ships would challenge and enrich the perspectives of planet-bound civilizations. This cross-pollination of thought and creativity would give rise to entirely new artistic movements and cultural norms, a true galactic culture that celebrates a diversity far greater than anything Earth has ever known. Biologically, the controlled exchange of genetic material seeds, animal embryos, and microbial life would allow for the terraforming of planets to proceed with a wisdom drawn from 1,000 different ecosystems. A barren world could be seeded with hardy lichen from one system, nitrogen-fixing bacteria from another, and fast-growing trees from a third, creating robust, hybrid biospheres engineered for success rather than relying on the limited palette of a single planet. This vision culminates in the most powerful safeguard for life itself, redundancy. On a single world, a planet-wide catastrophe, an asteroid impact, a supervolcano, or a self-inflicted disaster could spell the end for an entire species. But in a galaxy connected by a web of pathways, the failure of one node does not collapse the network. If a crisis were to strike the Earth, the civilization it spawned would live on, thriving on Mars, in the Jovian system, on Alpha Centauri, and in the Oort cloud. Humanity, or whatever we evolve into, would no longer have all its eggs in one planetary basket. The survival of intelligence, culture, and biology would be distributed across light years, making it virtually impervious to any single extinction event. This transforms our place in the universe from that of fragile inhabitants of a single, precious rock to that of a resilient, galactic species, actively participating in the long-term future of the cosmos. The ultimate promise of these invisible highways, therefore, is not merely faster travel. It is the creation of a future for life that is as enduring and interconnected as the stars themselves. Charting a course for this galactic future requires us to move from visionary concepts to a concrete, step-by-step plan. The sheer scale of the undertaking can feel overwhelming, but by breaking it down into a logical, generational timeline, we can see a clear and achievable path forward. This isn't a prediction of exact dates, but a reasoned projection of how the technology could mature, with each phase building directly upon the triumphs of the last, transforming the impossible into the inevitable. The first phase, unfolding over roughly the next 50 years, is all about achieving mastery within our own celestial backyard. This is the era of the interplanetary transport network coming into its own. We will witness a quiet revolution in solar system exploration, not with louder rockets, but with smarter navigation. The work will be done by a fleet of increasingly sophisticated, AI-powered probes, each one a testbed for the technologies we've discussed. These won't be one-off missions to single planets. Instead, imagine a coordinated effort where multiple small spacecraft are launched to act as a networked swarm. Their mission, to map the gravitational contours between the planets with unprecedented precision. One probe might be tasked with shuttling between the Lagrange points of Jupiter and its moons, creating a detailed gravitational survey of the Jovian system. Another might embark on a grand tour of the asteroid belt, using a complex series of gravitational assists to visit dozens of different objects, proving the efficiency of these pathways for resource prospecting. During this phase, the artificial intelligence running these missions will evolve from following pre-programmed scripts to making real-time decisions. It will learn to adjust its trajectory on the fly in response to tiny gravitational fluctuations or unexpected pockets of space dust, honing its cosmic intuition in the relatively safe environment of our solar system. Success in this phase is measured by the establishment of a reliable, frequently traveled network of routes between Earth, Mars, the asteroid belt, and the outer planets, turning the solar system into a well-connected archipelago and providing the operational confidence needed for the next, far greater leap. Building on a century of proven success within the Sun's gravitational sphere, Phase 2 begins around the year 2250 and involves humanity's first tentative steps onto the true interstellar highways. This era is defined by the launch of the first dedicated interstellar Pathfinders. These missions will target the very nearest stars like the Alpha Centauri system, a mere 4.3 light-years away. But the goal is not a desperate sprint, it's a patient, purposeful journey along the local galactic currents. These Pathfinder probes will be the direct descendants of the solar system explorers, but with crucial upgrades. Their AI will be vastly more advanced, capable of operating autonomously for centuries. Their sensor suites will include the pulsar timing arrays and quantum gravimeters we discussed, allowing them to navigate with confidence even when the Sun is just a particularly bright star among many. Their propulsion will be a hybrid system. Perhaps a powerful laser beam from a facility in the outer solar system gives them an initial push, after which they deploy a light sail to catch the solar wind. Once beyond the Sun's immediate influence, they will transition to pure gravitational sailing, their AI constantly scanning ahead to find the most efficient pathways through the local interstellar medium. The primary objective of these first missions is validation. Did our gravitational maps of the local galactic neighborhood, created by telescopes like LISA successors, accurately predict the pathways? The data these brave little scouts send back over a multi-decade communication delay will be priceless, refining our models for the larger missions to come. They are the equivalent of the wooden caravels that first mapped the coastlines of the New World, proving the route was navigable so that the larger galleons could follow. The third and most profound phase represents the full flowering of this technology, a millennium from now. By this point, the patient work of the Pathfinders has paid off. We will have not just a single route to one star, but a rudimentary web of pathways connecting dozens and then hundreds of star systems. This is when interstellar travel transitions from a heroic, one-way mission to an established, if still long-duration, endeavor. The spacecraft of this era will be true interstellar cruisers. Some will be robotic freighters, carrying vast quantities of raw materials mined from the asteroid belts of one system to the construction yards of another, where O'Neill cylinders and orbital habitats are being assembled. Others will be crewed vessels, though not necessarily generation ships in the classic sense. With advanced hibernation or life extension technologies, the same crew that departs from a hub at the Sun-Earth L2 point could awaken centuries later at a similar hub orbiting a star like Tau Ceti. The key development here is the establishment of infrastructure. The endpoints of these highways will no longer be empty points in space. They will feature communication relays, navigation beacons, and even refueling stations that harvest hydrogen from the local interstellar medium. This network won't be a rigid schedule. It will be a dynamic, flowing system with AI traffic controllers managing the complex dance of arrivals and departures at each nodal point. This phase marks the birth of a true interstellar economy and culture, where ideas, resources, and people circulate on a galactic scale, fulfilling the ultimate promise of the invisible highways. It's a project that spans generations, a testament to the power of long-term thinking, where the greatest voyages are begun by one generation for the benefit of those 1,000 years in the future. This newfound ability to navigate the galaxy using its own hidden infrastructure forces us to confront a profound shift in our own self-image. For our entire history, the universe has been a place of immense, forbidding scale, its distances a seemingly impenetrable barrier that rendered us isolated and insignificant. But if we learn to sail these cosmic currents, does that transform us from insignificant specks into masters of the galaxy? The answer is likely far more nuanced and humbling. It doesn't make us masters in the sense of conquering nature with brute force. Instead, it casts us in the role of astute students who have finally learned to read the universe's own instruction manual. We are not bulldozing a path through an untamed wilderness. We are learning the subtle rules of a road that was laid down billions of years before our planet even formed. This realization fosters a deep, profound humility. We are not the architects of these pathways, we are merely discovering them. Our greatness in this context lies not in our power to overcome the cosmos, but in our intelligence to understand and cooperate with its fundamental workings. It suggests a future where humanity sees itself not as a separate force battling the universe, but as an integrated part of a grand physical system, learning to move in harmony with its rhythms. This journey of discovery also opens up a possibility that is both thrilling and deeply unsettling, the chance that we are not the first to embark on it. The cosmic highways are not a human invention. They are a permanent feature of the galaxy, likely billions of years older than our species. If the physics is available to us, it would have been available to any other technological civilization that arose in the Milky Way. This leads to the captivating concept of interstellar archaeology. What might we find if we could read the signs along these ancient routes? The evidence would not be a crashed flying saucer on a planet's surface. It would be far more subtle, etched into the fabric of space itself. Perhaps our AI cartographers, while mapping the gravitational pathways, would discover anomalous sections of a route that are inexplicably clear of the micrometeoroid debris that should have accumulated over eons, as if something had regularly swept them clean. Or maybe, near a particularly stable and useful Lagrange point in a remote star system, our probes would find the faint, skeletal remains of a navigation beacon, its power source long dead, a silent testament to a voyage that ended millions of years ago. Discovering such artifacts would be one of the most momentous events in human history, instantly shattering our cosmic loneliness. It would tell us that intelligence is not a solitary flame, but a phenomenon that can flicker into existence multiple times across the galaxy, and that others, too, looked upon the stars and sought a way to journey among them. This prospect forces us to reconsider the very meaning of exploration. Traditionally, exploration has been about venturing into the unknown, charting blank spaces on the map where anything is possible. But what happens when we discover that the map has, in a sense, already been drawn by the laws of physics? Our paths are not random, they are the paths of least resistance, the ones that the universe itself has deemed most efficient. This introduces a fascinating paradox. Does this predetermined nature of the routes diminish the spirit of discovery, or does it elevate it? It shifts the challenge from one of sheer endurance to one of profound understanding. The explorer of the future is not a conqueror planting a flag on uncharted land, but a detective deciphering the clues left by nature. The adventure lies in the intellectual pursuit of uncovering these pathways and the skillful execution of navigating them. The unknown is no longer a geographic location, but a deeper layer of physical law and cosmic history waiting to be decoded. The journey becomes less about going where no one has gone before, and more about understanding a truth that has always been there, and perhaps following in the footsteps of those who understood it long ago. Ultimately, the development of cosmic highways connects our technological ambition to the most fundamental questions about our existence. Are we alone? What is our purpose in a vast, apparently physical universe? The ability to travel between stars does not provide easy answers, but it immerses us directly in the context where those answers might be found. It transforms philosophy from an abstract exercise into a practical, driving force behind our expansion. Every decision we make, from the ethical programming of the AI navigators to the choice of which pathways to explore first, becomes a statement about who we are and what we value as a species. This endeavor, therefore, is more than an engineering project. It is a rite of passage for humanity. It is our way of stepping onto the galactic stage not as conquerors, but as participants, ready to learn not just about the universe, but about our own place within its grand, intricate, and beautiful design. The vision of gliding along cosmic currents is undeniably elegant, but we must temper this grandeur with a clear-eyed look at the monumental obstacles standing between us and that future. These are not minor engineering puzzles. They are fundamental challenges that strike at the very core of physics, biology, and human endurance. To understand the true scale of the endeavor, we can group these hurdles into three formidable categories: the technological, the energetic, and the biological. Each represents a frontier of innovation we must cross. First, the technological challenges demand a leap in reliability that dwarfs anything we have ever achieved. We are not building a smartphone or a car designed to last a decade. We are crafting systems that must remain flawlessly operational for centuries, even millennia, in the most hostile environment imaginable. Consider the artificial intelligence at the heart of the mission. It must be more than just intelligent. It must be robust beyond comprehension. We are asking this digital mind to process trillions of calculations without a single critical error over time spans longer than the existence of some nations. Cosmic radiation can cause bit flips in computer memory, gradually corrupting its programming. The solution isn't just better shielding. It may require entirely new computing architectures, perhaps based on self-correcting quantum error correction or massively redundant systems that can repair themselves. Then there are the materials. The spacecraft's hull will be bombarded for centuries by micrometeoroids traveling at relativistic speeds. We need materials that can self-heal, or composites so advanced they can absorb these impacts without compromising the vessel's integrity. Every single component, from the smallest sensor to the largest structural beam, must be engineered for a lifespan that is currently unimaginable, pushing the science of material durability to its absolute limits. The second category, the energetic challenge, is a problem of sheer endurance. How do you power a civilization in a can for 1,000 years? The power source must be incredibly reliable, incredibly dense, and able to function far from the warmth of the sun. Our current solutions fall short. Solar panels become useless in the deep dark between stars. Chemical fuel is out of the question for such a long duration. Radioisotope thermoelectric generators, like those used on the Voyager probes, provide steady power but eventually decay, their output dwindling over time. The most plausible answer lies in advanced nuclear fission reactors, small and safe enough to be launched but powerful enough to provide electricity for centuries. The ultimate goal would be compact fusion reactors, essentially bottling a miniature star to power the journey, but even that might not be enough for the needs of a large crew. The energy requirements extend beyond just keeping the lights on. They power the AI's constant computations, the sensors scanning the void, the communication laser sending faint whispers back to Earth, and the delicate thrusters for course corrections. This is not just about generating power, it's about managing and storing it with near-perfect efficiency over geological timescales, a feat that demands breakthroughs we are only beginning to glimpse. Perhaps the most intimate and profound challenge is the biological one. If we intend to send living beings, whether awake or in suspended animation, we are confronting the very nature of life itself over cosmic time. For a crude generation ship, the biological system is as complex as the spacecraft. You need a perfectly balanced, closed-loop ecosystem that can recycle air, water, and nutrients indefinitely. On Earth, our biosphere has had billions of years to achieve its balance. We must replicate that stability within the confined walls of a ship. A single crop failure, a plague among the livestock, or a subtle imbalance in the atmosphere could doom the entire mission. Then there is human biology itself. Prolonged exposure to even low levels of cosmic radiation dramatically increases cancer risks and could cause cumulative damage to the brain and other vital organs. We would need revolutionary medical technologies, perhaps even genetic enhancements, to bolster human resilience, and we cannot ignore the psychological dimension. How does a human mind cope with being born, living, and dying inside a metal can, knowing that the destination is generations away? The social structures required to maintain a stable, purposeful society over such a span are a sociological experiment without precedent. Yet, it is vital to frame these challenges not as impossibilities, but as a set of complex, interconnected problems waiting for solutions. This is precisely the mindset that fueled the Apollo program. In the early 1960s, going to the moon seemed an almost mystical goal. The challenges building rockets powerful enough, navigation systems accurate enough, and life support systems reliable enough were considered by many to be insurmountable within the decade. But President Kennedy framed it not as a single, impossible leap, but as a series of difficult tasks that would organize and measure the best of our energies and skills. That is the model we must adopt for interstellar travel. We are not waiting for one magic bullet. We are embarking on a grand, multi-generational project where each breakthrough in material science, each advance in AI reliability, and each new discovery in closed-loop life support brings the stars incrementally closer. By acknowledging the sheer scale of these obstacles, we do not diminish the dream, we make it more credible. We replace fantasy with a concrete engineering roadmap, a challenge worthy of the greatest minds for centuries to come. This honest assessment is what separates a sustainable vision from mere science fiction, grounding our celestial aspirations in the hard but solvable problems of reality. While the gravitational highway network offers an elegant and physically sound method for traversing the galaxy, the sheer scale of interstellar distances, even when traveled efficiently, presents a final, formidable frontier: time. A journey to the nearest stars riding the cosmic currents would still span centuries. This inherent limitation of sub-light travel naturally pushes our imagination toward more radical solutions, concepts that sound like they belong firmly in the realm of science fiction, but are, in fact, grounded in the same theory that gives us the highways themselves, Einstein's general relativity. These are the breakthrough ideas that dare to ask if we can not just navigate the fabric of space-time, but manipulate it directly to overcome the ultimate speed limit of the universe. The most iconic of these concepts is the wormhole, often visualized as a tunnel or shortcut connecting two distant points in space-time. Imagine the universe as a vast, flat sheet of paper. If you wanted to get from a point at the top to a point at the bottom, the conventional way is to travel the long distance across the surface. But if you could fold the paper so those 2 points touch, and then punch a hole through the connection, you've created a wormhole, a bridge that reduces a journey of thousands of light years to a mere step through a doorway. The mathematics of general relativity does not forbid such structures. Certain solutions to Einstein's equations, like the Einstein-Rosen bridge, describe them. However, there are colossal challenges. Theorists believe that naturally occurring wormholes, if they exist at all, would be microscopic, unstable, and would collapse the instant anything, even a single photon, tried to pass through. To make a wormhole traversable for a spacecraft, we would need a form of matter or energy with negative mass or negative energy density, often called exotic matter, to prop the throat of the wormhole open against the force of gravity that wants to snap it shut. While exotic matter is not entirely a fantasy, a tiny quantum effect known as the Casimir effect demonstrates negative energy densities in a lab. The amounts needed to stabilize a wormhole large enough for a ship are astronomical, far beyond any technology we can conceive of today. A wormhole would be the ultimate express lane on our cosmic highway system, a fixed tunnel allowing for instantaneous travel between two specific points, but building it would require a mastery over physics that borders on the godlike. A different yet equally mind-bending approach is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Instead of creating a tunnel, this concept involves warping the space around a spacecraft itself. Think of it not as a ship moving through space, but as a ship riding a wave of space-time. The Alcubierre drive would create a bubble of flat space around the vessel. In front of the ship, space-time would be compressed, pulling the destination closer. Behind the ship, space-time would be expanded, pushing the point of origin farther away. Inside this bubble, the spacecraft would be motionless relative to its local space. It's the space itself that is moving, carrying the ship along like a surfboard on an ocean wave. Since the ship isn't accelerating within the bubble, it would avoid the relativistic effects and crushing g-forces associated with near-light-speed travel. Most strikingly, within the framework of general relativity, this warp bubble could, in theory, move faster than light without violating Einstein's laws, because the information of the ship itself is not moving faster than light through local space. The expansion and contraction of space-time is what is propagating. The catch, once again, is the requirement for exotic matter with negative energy density to generate the warp field. Current estimates suggest the energy requirements are equivalent to converting the mass of Jupiter, or even a large star, into pure energy, making it just as fantastical as the wormhole with our current understanding. It is crucial, however, to view these spectacular ideas not as replacements for the gravitational highway concept, but as potential technologies that could one day be integrated with it. They represent different chapters in a future playbook for galactic exploration. The invisible highways provide the foundational, low-energy infrastructure for becoming a true solar system-wide and then local interstellar civilization. They are the system of country roads and interstate highways that connect towns and cities across a continent. Wormholes and Alcubierre drives, should they ever become feasible, would be the transoceanic jets and supersonic transports, specialized, high-energy technologies for making immense leaps across the voids that separate major hubs. You might use a gravitational pathway to travel efficiently from Earth to a major industrial hub at the Sun's gravitational focus, hundreds of times farther than Pluto. From there, you could enter a stabilized wormhole or engage a warp drive for a quick jump to a similar hub in the Alpha Centauri system, bypassing the multi-century journey through ordinary space. In this vision, the highways don't become obsolete. They become the essential feeder network that connects populated worlds to the grand interstellar transport terminals. This forward-looking perspective is vital because it keeps our vision dynamic and adaptable. The history of technology is a story of paradigms shifting in unpredictable ways. The engineers who perfected the sailing ship could not have imagined the jet engine, yet both forms of transport coexist and serve different purposes today. By seriously investigating the outer limits of theoretical physics, we are not abandoning the practical, near-term potential of gravitational sailing. We are ensuring that if a revolutionary breakthrough does occur, we will have the foundational knowledge and infrastructure ready to embrace it. It acknowledges that the ultimate future of space travel may not be a choice between one technology or another, but a sophisticated synthesis of many. We may learn to ride the gentle cosmic currents for local travel, harness focused beams of energy for boosting probes, and one day, perhaps, learn to tie knots in space-time itself for the ultimate shortcuts. This openness to possibility, grounded in rigorous science but unafraid to explore the farthest edges of what might be allowed by the laws of nature, is what will ultimately propel humanity from being residents of a single world to citizens of an entire galaxy. The true power of these interstellar highways extends far beyond mere transportation. It lies in their potential to ignite the most profound scientific revolution in human history. For centuries, science has been a prisoner of a single, fixed vantage point. We have been like an astronomer confined to one room, trying to understand the entire universe by peering through a single, stationary window. Every observation, every measurement of an exoplanet's atmosphere or a distant galaxy's behavior is filtered through the unique and limited perspective of our solar system. But the moment we can place scientific instruments and eventually human researchers at multiple points across the galaxy, that single window swings open to reveal an entire observatory with a 360-degree view. This distributed network of intelligence will transform every field of science, answering questions we can currently only guess at and uncovering mysteries we haven't even thought to ask yet. The most immediate and dramatic transformation will occur in the field of planetary science. Right now, the study of exoplanets is an exercise in extreme indirectness. We infer the presence of a planet by the slight dimming of its star as it transits, or by the tiny wobble its gravity induces. We analyze its atmosphere by painstakingly studying the starlight that filters through it. It's like trying to identify a person standing behind a frosted glass door by the shadow they cast and the faint sound of their breathing. But with interstellar highways, we can send probes directly into these alien star systems. Imagine the wealth of knowledge that would flood in from having even a simple robotic orbiter around 100 different Earth-sized worlds. We could move from speculation to comparative planetology on a grand scale. We could finally answer fundamental questions about planet formation. Why do some rocky worlds become hellish greenhouse effect infernos like Venus, while others become frozen deserts like Mars, and a rare few become temperate havens like Earth? Is it simply their distance from the star, or do factors like the intensity of stellar flares, the presence of a large moon for stabilization, or the timing of planetary migration play a more critical role? By comparing the geology, atmospheric composition, and magnetic fields of hundreds of worlds, we would be able to construct a true statistical model of planetary evolution, turning what is now a collection of individual data points into a rich, understandable narrative. This would tell us with concrete evidence whether Earth is a cosmic fluke or a common outcome under the right conditions. This direct access would supercharge the search for life. Our current methods for detecting biosignatures, like the combination of oxygen and methane in an atmosphere, are prone to false positives, as geological processes can sometimes mimic biological ones. But a probe in the system could conduct a far more sophisticated analysis. It could measure isotopic ratios in the atmosphere that are almost exclusively shaped by biological activity. It could scan the surface for the distinctive light signature of chlorophyll or other alien pigments. It could even deploy landers to analyze soil and water samples directly. The discovery of even simple, single-celled life on a single exoplanet would be epoch-making, but discovering it on several, or finding entirely independent branches of the tree of life, would answer the ancient question of life's prevalence in the universe. It would tell us that life is not a fragile, unlikely accident, but a natural and robust force that emerges wherever conditions permit. Conversely, finding a galaxy full of sterile, albeit Earth-like, planets would be equally profound, forcing a radical reconsideration of our own planet's uniqueness and the specific chain of events that led to us. Beyond planetary science, the highways would revolutionize astrophysics itself. By distributing observatories across thousands of light-years, we would gain the ultimate tool, a galaxy-sized interferometer. An interferometer works by combining the light from multiple telescopes separated by a distance, effectively creating a single virtual telescope with a resolution equal to that distance. Right now, our largest interferometers are on Earth, giving us the resolution of a telescope the size of our planet. But imagine an array of radio telescopes positioned in different star systems, separated by light years. The resolution would be so unimaginably sharp that we could, in principle, map the surface of a neutron star in exquisite detail, or peer directly into the chaotic accretion disk of a supermassive black hole at the center of a distant galaxy. We could watch stars being born in dense nebulas with a clarity that would make current images look like abstract paintings. This stereo vision would also allow us to create a precise three-dimensional map of the Milky Way, finally nailing down the distances to far-flung stars and clusters with absolute certainty, and giving us a definitive understanding of our galaxy's large-scale structure and motion. Perhaps the most profound application of this distributed network would be in the study of the universe's most violent and energetic events. When a star explodes as a supernova or two neutron stars collide, they send out not only light but also gravitational waves, ripples in space-time. Our current gravitational wave detectors on Earth can sense these cataclysms, but with only a handful of detectors in one location, pinpointing their exact origin in the sky is like trying to locate a single speaker in a crowded stadium with your eyes closed. With detectors spread across the galaxy, we could triangulate the source of a gravitational wave with pinpoint accuracy. The moment an alert went out, every telescope in the network, optical, X-ray, radio, could instantly slew to the exact coordinates, capturing the event in every part of the electromagnetic spectrum from its very first moments. This multi-messenger astronomy, combining gravitational waves with light, would give us a complete picture of these cosmic engines, revealing the physics of matter under the most extreme conditions imaginable. It would be like having front-row seats to the most spectacular shows in the universe, with a backstage pass to understand how they work. This unparalleled access to knowledge, the ability to not just witness but truly comprehend the cosmos, provides a unifying purpose that transcends national borders and generations, uniting humanity in the greatest collaborative project it has ever undertaken. The sheer magnitude of this undertaking, spanning centuries and demanding breakthroughs across every field of science and engineering, reveals a fundamental truth that transcends technology itself. Constructing the invisible highways of the cosmos is not a challenge that can be met by a single nation space agency, a lone billionaire's vision, or even a consortium of the world's wealthiest corporations. This is a project that belongs to humanity as a whole, an endeavor that will require a level of global, multi-generational collaboration unlike anything we have ever attempted. It demands that we pool not just our financial resources, but our collective knowledge, our cultural wisdom, and our shared willpower. This is not merely about building spacecraft. It is about building a common purpose that can span continents and centuries, uniting us around a goal that is both profoundly peaceful and inherently inspiring. We can find powerful echoes of this collaborative spirit in our own history, in projects whose scale seem to defy the limitations of their time. Consider the great Gothic cathedrals of Europe, like Notre Dame de Paris or the Duomo in Milan. These were not projects completed in a single lifetime. The architects who drew the original plans knew they would never walk beneath the finished vaulted ceilings. The stonemasons who laid the foundation stones understood that their grandchildren would be the ones to place the final spire. Yet they worked with unwavering dedication, driven by a shared faith and a vision that extended far beyond their own mortal span. The construction of these cathedrals required the coordinated effort of entire communities: quarrymen, carpenters, glassmakers, and laborers, each contributing their specialized skill to a masterpiece that would define their city for 1,000 years. The Interstellar Highway project is our modern cathedral, but on a planetary scale. It is a testament we are building not to a deity, but to the enduring curiosity and potential of our own species, a monument whose architecture is woven into the fabric of space itself, and whose construction will require the dedication of generations of engineers, scientists, and dreamers. This perspective transforms the entire endeavor from a cold, technical problem into a potential catalyst for human progress. In a world often fractured by political disputes, economic competition, and cultural differences, the goal of reaching the stars presents a rare and powerful unifying objective. It is a challenge that is fundamentally peaceful and cooperative by its very nature. No single country can claim ownership of a Lagrange point or a gravitational pathway. These are natural features of the universe, as common to humanity as the air we breathe or the oceans we share. To navigate them successfully, we will need a global network of observatories sharing data in real time, international treaties ensuring safe passage, and a shared pool of scientific knowledge that accelerates discovery for everyone. The very process of negotiating these frameworks, of learning to trust one another with a project of such immense importance, could forge new bonds of international cooperation. The mission to map and travel the cosmic highways could become the crucible in which we finally learn to set aside our terrestrial squabbles and work together as a single species with a shared destiny among the stars. This collaborative spirit must extend beyond governments and space agencies to embrace the full spectrum of human creativity. The algorithms that will guide our autonomous ships will benefit from the insights of computer scientists in Bangalore as much as from those in Silicon Valley. The advanced materials needed for century-long voyages will be developed in laboratories from Munich to Tokyo. The psychological and sociological models for a multi-generational crew will draw upon the wisdom of anthropologists, historians, and artists from every culture on Earth, ensuring that the society we send into the void is resilient, adaptable, and richly human. This is not a project that can be siloed. It is a tapestry that must be woven from every thread of human knowledge and experience. By embracing this inclusive, global effort, we do more than just increase our chances of technical success. We ensure that the future we are building among the stars is a reflection of all that is best about humanity, our ingenuity, our diversity, and our capacity to aspire to something greater than ourselves. This unifying journey, therefore, becomes its own destination, a process that elevates us even as we reach for the heavens. But this grand vision of a galaxy connected by invisible highways is not a future that will build itself. The spacecraft, the artificial intelligence, the intricate gravitational maps, all of it will be conceived, designed, and brought to life by human minds. And that means the single most critical component of this multi-generational project is not a piece of technology, but an investment we make today in the curiosity and intellect of the next generation. The children who are today marveling at pictures from the James Webb Space Telescope or building simple robots in their classrooms are the very same individuals who will, in a few decades, be the mission planners, the engineers, and the navigators of the first true interstellar voyages. Our responsibility, therefore, is to provide them with the tools, the inspiration, and the foundational knowledge they will need to turn this incredible dream into a working reality. This begins with a renewed and passionate commitment to education in science, technology, engineering, and mathematics, the essential STEM fields. But this cannot be the dry, rote memorization of formulas that sometimes characterizes these subjects. We must reframe STEM education not as a series of difficult hurdles, but as a set of superpowers for solving the universe's greatest puzzles. Instead of just teaching Newton's laws of motion, we can challenge students to use them to plot a course for a probe swinging past Jupiter. Rather than presenting calculus as an abstract concept, we can show how its principles are the language of orbital dynamics, allowing us to predict the position of a spacecraft decades into the future. The vision of interstellar travel provides a powerful, tangible, and thrilling context for learning. It answers the perennial question students so often ask: when will I ever use this? With the most inspiring answer possible, you could use it to navigate to another star. This approach transforms the classroom from a passive lecture hall into a mission control center in training, where every math problem solved and every physics concept mastered is a step toward building a future among the stars. The dream of the invisible highways is uniquely suited to be a catalyst for interdisciplinary learning, breaking down the artificial barriers we often place between subjects. To truly understand these cosmic pathways, a student must grasp not only physics and mathematics, but also computer science for the AI navigation, materials engineering for the durable spacecraft hulls, and even biology and psychology for sustaining life on long-duration missions. An art student might be inspired to design the interfaces for the AI navigator, requiring an understanding of human-computer interaction. A history student could analyze the societal impacts of previous great explorations, like the Age of Sail, to help model the social structures needed for a generation ship. This vision demonstrates that grand challenges are never solved by a single specialty working in isolation. They demand a symphony of diverse talents, all harmonizing around a common, awe-inspiring goal. By presenting education in this integrated way, we show young people that their unique passions and skills, whether in coding, writing, or designing, all have a vital role to play in the greatest adventure humanity has ever conceived. Fostering this mindset requires more than just a revised curriculum. It demands a cultural shift in how we portray science and exploration. We need to celebrate not only the triumphs, but also the fascinating process of failure and iterative problem solving. The story of the interstellar highways is filled with complex, unsolved problems: how to build a self-healing material, how to create a truly robust artificial intelligence, how to maintain a stable society for centuries. We should present these not as insurmountable barriers, but as open invitations, as cosmic riddles waiting for a solution. Imagine science fairs where students compete to design the most efficient light sail, or hackathons where teams develop algorithms to navigate a simulated gravitational landscape. By engaging with these problems early, we cultivate a generation of intuitive problem solvers, individuals who don't see a dead end but a spectrum of possibilities. This is about nurturing a specific kind of courage, the intellectual bravery to tackle questions that do not have answers in the back of a textbook, because the answers have not yet been discovered by anyone. Ultimately, this endeavor brings our narrative full circle, from a distant future thousands of years from now back to the present moment, and to the choices we make in our classrooms, our libraries, and our homes. The dream of sailing the cosmic currents is not just a destination to be reached, It is an engine for human progress here and now. It provides a positive, unifying, and monumental goal that can inspire a young person to push the boundaries of their own potential. The students who are inspired by this vision will not only be the architects of the interstellar age, they will also be the doctors who develop new medical technologies, the engineers who build sustainable cities, and the innovators who solve the pressing challenges of our time. The skills needed to chart a course to Alpha Centauri are the very same skills that will propel our civilization forward on Earth. By planting the seeds of this interstellar ambition today, we are not just investing in a future among the stars, we are investing in a brighter, more capable, and more hopeful future for humanity itself, ensuring that the next generation is equipped not only to dream of the cosmos but to actively, skillfully, and gracefully journey into its vast and waiting depths. We began with the image of invisible highways woven into the fabric of space itself, and we have journeyed together through the physics that creates them, the technology that will map them, and the profound implications of learning to sail upon them. These pathways are not science fiction, they are a natural and permanent feature of our universe, as real as the orbits of the planets and the gravity that holds us to the ground. They have existed for billions of years, silent and waiting, not for us to build them, but for us to finally develop the wisdom to see them. The development of this capability, of becoming cosmic sailors rather than cosmic bulldozers, represents one of the most ambitious and transformative projects humanity could ever undertake. It is a challenge that stretches across centuries, demanding not just technological leaps but a fundamental evolution in how we see our place in the cosmos. This endeavor promises to open the galaxy not to our conquest, but to our curiosity and our enduring spirit of discovery. The road to the stars is undeniably long, a journey measured in generations rather than years. But for the first time in history, we can say with confidence that it is not uncharted. The map for this greatest of voyages is not drawn on paper. It is written directly into the laws of physics, etched into the curvature of space-time by the gravity of stars and the dark matter flowing between them. Our task is not to invent a path, but to learn to read this cosmic scripture, to translate the subtle mathematics of general relativity into a practical guide for navigation. The greatest voyage in human history no longer seems like a distant fantasy, but a systematic, step-by-step process that begins with the Pathfinder missions in our own solar system and extends, link by link, into the galactic web. It awaits its navigators, its engineers, its cartographers, and its dreamers. If this vision of a connected galaxy, of a future where humanity takes its place among the stars, has sparked your imagination, then you are already part of this incredible story. This channel is dedicated to exploring the ideas that will shape our destiny, from the invisible highways of space to the artificial intelligence that will guide us along them. Subscribe to join us on this continuing journey of discovery, and we are truly curious to know what you think, which aspect of interstellar travel captures your imagination the most. Is it the sophisticated AI navigators, the mind-bending physics of gravity, or the profound idea of a generation's ship becoming a world unto itself? Let us know in the comments below. Your thoughts and questions help fuel this conversation about our future. Thank you for watching.